Welcome back, Physics 30. So in the previous video, we talked about this new force, this strong nuclear force that is overcoming this huge, was 9.21 newtons, but this huge electrostatic force that is holding two protons together because gravity can't do it. So there must be another force that does it. So this other force is called the strong nuclear force. And where this comes from, it comes from what we call binding energy, energy that is created when you put more than one proton and nucleus together into a nucleus. Right? So I say more than one because one proton is just the mass of a proton. But as soon as you put a proton and a neutron together, all of a sudden those protons and neutrons, they lose mass. And that lost mass becomes energy that holds the nucleus together. It's called the binding energy. Now, so that's, you could look through here. It says removing a nucleus from a stable isotope requires energy because work must be done to pull it out. And when you do that, you are technically adding energy to that nucleus or the nucleon, and that energy becomes mass. But when you put it back in there, that mass goes back to becoming energy. So this is the binding energy that holds it together. Now we can find that binding energy by looking at the energies of all the nucleons, like individually, right? And then the energy of them all together inside the nucleus, and then subtracting the two, right? That's not too bad. Okay, so how do I find the energies of all these nucleons and all of these nucleus, or nucleons and the energy of the nucleus? Well, to do that, we just had to find the mass of those things. Okay? So in a nuclear reaction, this involves conversion between mass and energy. And there's a famous formula that deals with this, right? Where I could say E is equal to mc squared. So that comes back again, right? So if I lose energy, it becomes mass, or if I lose mass, it becomes energy based on this formula. So I can just rearrange this. Maybe I should write it out properly. So I can just rearrange it to find one of the missing pieces that we're looking for here, right? So we're just going to be looking at the masses, the difference between the masses, and then I can use that to find the binding energy, okay? So the difference in the mass, what we call a mass defect. We've lost mass between the two sides. I don't know if that's in here somewhere. No, it isn't. Okay. So right here, it says rearranging Einstein's equation, you're doing all this other stuff. We can create this, a formula that just says the change in the mass is equal to the number of nucleons minus the mass, the mass of the nucleons minus the mass of the nucleus. There's going to be a difference between the two sides. So you're just taking this formula here, you're just replacing everything with m and c squared. So you can go like this up here. M is equal to, oops, sorry, E is equal to mc squared. Mc squared minus mc squared, right? So all of these energies could be mc squared. This mass would be the mass of the nucleus. This mass would be the mass of all the nucleons individually. And this would be the mass, what we call the mass defect. I'm just going to write that on the bottom of this a little bit larger. So this would be the mass defect right there, okay? If we divide everything by c squared, boop, 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 you end up with just the formula down here. You can see down here what we have here. The mass of the nucleons minus the mass of the nucleus gives us our mass defect. Okay? So how much mass have we lost when we put these nucleons together? Okay? And then that mass then can be changed into a binding energy. How much energy is actually being used to hold these together? Later on we'll talk about this. That energy is actually changed into gluons, a very specific type of particle that's related to or responsible for the strong nuclear force that we're talking about here. Okay? So to do this, we're going to have to determine, it's a multi-step process. We're going to determine as precisely as possible the mass of all the nucleons and the mass of the carbon-12 by itself. Okay? So the mass of the nucleons, no, never mind. The mass of the nucleons in carbon-12, there are 12 pieces in there. We got 6 protons, and we have 6 neutrons. Okay? Now you have to treat these as if they're all separated, so they're not together. So there's like 6 of these guys just kind of sitting there. There's 6 of these ones here. I'll call them the protons. Solid dots here. Okay, so the mass of 6 protons is just 6 times the mass of a proton. The mass of a proton here. Let's do this in kilograms because it makes it a little bit easier to do the conversion. E is equal to mc squared. And that formula has to be in kilograms. So 1.672622. You want to do this as precise as possible, so we're going to use all the decimals down there. And the number of neutrons is 6 times 1.674927 times 10 to the negative 27 kilograms. Okay? So I'm going to add these together, and we're going to get the mass of all the individual pieces. Plus 6 times 1.674927 e to the negative 27. So I get a mass. I hope I did this correctly. And 6 times that. Let me just double check. 6 times that, yeah, it looks pretty good. Okay, so I get a mass of 2.0085294 times 10 to the negative 26 kilograms. Okay, so that's the mass of everything separated. The next part of this is we want to find the mass if everything was together. So I'm just going to draw a line here. Okay. So the mass of everything together. So this is now the nucleus here, which has 6 protons and 6 neutrons. All together in this little bubble, right? Now, when they're inside this bubble, the mass slightly changes. And by definition, carbon-12 is 12 atomic mass units. So 12 U's. So we're just going to use the conversion factor of what a U is. So a mass of this now is 12 times 1.66. I'm going to go up here just a second. Find the actual number. We used up here 660,539. 0.539 times 10 to the negative 27 kilograms. So let's do that math really quickly here. 12 times 1.660539 times 10 to the negative 27. So I get a mass of 1.9926468 times 10 to the negative 26 kilograms. Okay. So those masses, you can see right now, their masses are not the same. The mass of the individual pieces is more than the mass of them put together. Okay, so the mass defect now, so my mass defect is going to be the difference between these two. It doesn't matter if it's positive or negative. We're just going to make it positive, but in this case, it's going to be the mass of the nucleons, which is going to be the bigger number, the 2.00. I'm going to just pull my calculator here. I use my numbers in my calculator. 5,294 times 10 to the negative 26 minus the mass of the nucleus, which is smaller. You're going to see later on, we're going to do a very similar calculation when we talk about energy released in nuclear reactions. Let me just do this. So we get a mass defect of 1.58826 times 10 to the negative 28 kilograms. Okay, so we lost mass. This is how much mass we've lost. Now that mass that's been lost is being changed into binding energy, and we just calculate that by going E is equal to mc squared. So I'm going to do this 1.588 number and times it by the speed of light squared. I'm not going to write that out. So times it by speed of light squared. And that's going to give us 1.43 times 10 to the negative 11 joules. We always get joules out here because we use kilograms. We're going to get joules out. And what I'm going to do with this number is I'm going to change it into electron volts. Now, when you do this, you change it into electron volts, you're going to get this big number. So I'm dividing by the electron volt number, 1.6 times 10 to the negative 19. That's how many joules per electron volt. It's on your formula sheet. So we get 8,933,9625 electron volts. What I'm going to do is I'm going to just change this into 6 mega electron volts. Whenever you're talking about the subatomic stuff, you always like to use electron volts for communication purposes, like I said before. So I just moved this over 6 places. 1, 2, 3. That'd be kilo if it was here. That'd be kilo. 3 mega. If I went 3 more, I'd have giga. That might show up a couple of times later on. There we go. So all that energy is technically being transformed into these gluons, these force-carrying particles, these massless particles, very much like photons. They don't have mass, but they do interact with matter, and they cause this strong nuclear force. It's pretty cool. Okay. I'm going to stop this video here, and I'll come back the next video. See ya.